Hi guys, welcome back to our channel Unknown IITians. Today we are going to discuss the topics one-to-one functions, exponential functions, natural exponential functions, composite and inverse functions. So now let's get started. First, one-to-one function, which is also termed as injective function. Okay? So basically what is a one-to-one function? A function in which every element in the domain maps to a unique element in the codomain. This is the definition basically. Element in the codomain. See here the word uniquely. The unique. Okay, this decides whether it is one-to-one function or not. So here the every element in the domain maps to a unique element in the codomain. Okay, let's see few examples to understand it better. I have two examples. First one is f of x is equal to root x, and the second example f of x is equal to x square. Okay, so now let us consider the domain. Here suppose let's think we have elements like 1, 4, 9 and 16. Here we are having 1, 2, 3 and 4. See here 1 maps to 1, 4 is mapping to 2, 9 is mapping to 3, 16 is mapping to 4. That means every element in the domain, this is domain and this is codomain. So every element in the domain is mapping to a unique element in the codomain. So this is a one-one function for this domain and codomain respectively. Okay, this is square. So now let us consider another example. Here this is the domain and this is the codomain. Okay, here we are having elements like -1, -2, 0, 1 and 2. Here we are having 1, 4, 0, 9. Now see, -1 will map to 1, 1 also maps to 1. -2 will map to 4 and 2 also maps to 4. 0 maps to 0, okay? So now see here, -1 and 1 both are mapping to 1 and -2 and 2 both are mapping to 4. So here the elements in the domain are not mapping to unique elements in the codomain. That means this is not a one-to-one or injective function in this particular domain and codomain. Okay, this is how you have to check whether a function given is one-to-one or not. Okay, now let's see what is vertical line test. Okay, this is a test performed to graph given whether to determine it is a function. The graph represents a function or not. Okay, let me write it more clearly. Whether the graph represents a function or not. Okay, basically what we do in this test is, if for suppose we are given a graph like this, see in this example here, when we draw a vertical line, see here the line is touching the graph at 2 points. Okay, if this happens, the graph fails the vertical line test. If a graph fails vertical line test, then that means the function is not the graph is not a function. Okay, let's see why this happens. According to the definition of function, every x value should map to a single y value. That means x1 maps to y, x2 can also map to y, but x1 mapping to y, x1 is x1 mapping to y1 and x1 also mapping to y2. This should not happen. This should not happen according to the definition of function. So, if we draw a vertical line for a graph, if there are two intersection points, then that means there are two different y values for a unique x value. So, here the definition of function is not getting satisfied. That is the reason if a function, if a graph fails the vertical line test, then we say it cannot be a function. Okay. See, let me give you an example. Previously, we have seen a graph in the previous slide. The graph is something like this. Okay, this is something. Yeah, this is how the graph is in the previous one. Here we are having two intersections. These intersections are along y-axis. See here, the x value is same, but the y values are different. For instance, let us consider an example like this. What if we are having a graph like this? Can you say this is a function or not? Simple, performing vertical line test. You can draw the vertical line at any point of the graph. See here, there is only unique point of intersection. Okay, that means this is a function. So basically the intersection must be unique when we draw a vertical line. Okay, this is how we can check when we are given a graph whether it is a function or not. This is one of the methods to check whether this the graph represents a function or not. Now let's discuss what is horizontal line test. This horizontal line test is performed to determine whether the function is one-to-one or not. Okay, this horizontal line test is used to determine whether the function is one-to-one or not. So see here the examples, you can understand them betterly now. See, for example, this is the graph given for a particular function. This is graph of x square function. Okay, now if we draw horizontal lines, see here the intersection of this line with the graph is not unique. It is not intersecting at exactly one point. Here we are having 2 points of intersections. That means this f of x equal to x square is not a one-to-one or injective function. Okay, this is how we determine whether the graph is one-to-one, whether the given graph is a graph of function one-to-one or not. We use horizontal line test to determine it. If we draw horizontal lines along the graph and we see there is intersection between more than 2 points, then we say that it is not a one-one function. Now let's see an example of one-one function. See, for example, we are having something like this. The graph is like this. Wait. Yeah. So basically this is y is equal to x cube graph. Now let's draw the horizontal lines. You can draw as many as you can. See, there is unique intersection. Here there is only one point of intersection. So that means this is a one-one function. Basically, the vertical line test is used to determine whether the graph represents a function or not. But horizontal line test, it helps us in determining whether the function is injective or not. Okay, now what is an exponential function? So basically, exponential function, this is a mathematical function which we represent in the form of a into b power x. Don't get confused. This is the exponent. This is the base, and this is some constant. Okay, so here we are multiplying this constant with the base. Okay, this is exponent, base, and constant. This is how a basic exponential function look like. Now these exponential functions are having some properties and some laws. Let's discuss what are those. For example, you are given x power m into x power n. Remember here x and x, the bases are same. Okay, then you can write this as x power m plus n. See here we are adding m and n. Okay, this is the first law. And for example, here you are given x power m by x power n. See here also the bases are same. Then this can be written as x power m minus n. And the power rule. See, for example, here you are given x power m whole power n. Okay, this can also be written as x power m n. And similarly, x by y whole power m is x power m by y power m. And here this is very important, the zero power rule. Any base to the power of 0 will be equal to 1. Okay, except 0. Remember this, except 0. For any base except 0 with exponent 0, the value will be equal to 1. Okay, and for example, suppose we are having x power minus n, then this can be written as 1 by x power n. So now let us see some examples so that you can understand them more clearly and in a better way. For example, we are given 2 power m into, okay, let me take this also as a number, something like 2 power 2 into 2 power 4. See, as we have discussed before, the bases are same. That means this can be written as 2 power 2 plus 4, that is 2 power 6. Similarly, if we are given 2 power 4 by 2 square, that means 2 power 4 minus 2, that is 2 square. For example, we are given 2 by 4 whole power 6. This can be written as 2 power 6 by 4 power 6. Or we are given 2 into 3 whole power 6. That means this can be written as 2 power 6 into 3 power 6. For suppose we are given 2 power minus 4. This can be written as 1 by 2 power 4. Similarly, anything power 0, this can be 2, x can be 2, x can be 1, x can be 3, and so on. X can be anything except 0. The value will be equal to 1. Okay, this is how you have to use the basic laws of exponents to solve a problem. So you will be given, you are not simply asked to determine this 2 square into 2 power 4. Nobody is going to ask you that basic thing. You must be able to apply all these formulas, all these concepts whenever required. You have to practice more and more problems to get more clarity and idea when and where to use the formulae. Okay, next. So now let's discuss what is a natural exponential function. Simple. We know how to represent an exponential function. It's a into b power x. In the natural exponential function, the base is always fixed. The base is e only. Okay, the natural exponential function is of the form e power x. Okay, see here the base is e, and this e is an irrational number. E is an irrational number, and it is having an approximate value as 2.71. Okay, this is how the graph of exponential function look like. See here, we are having some properties. For these special, like for the natural exponential functions. Remember, natural. First thing, the function is 1 to 1. Okay, you will have a unique value of e of x for every different x value. Okay, for if this is unique, okay, let me write it reversely, then you can understand it better. If this x value is unique, then automatically this e power x value will be unique. So this is a 1 to 1 function always. Similarly, e power 0 is 1, and the domain of this function, see, x can be anything. Okay, x can be anything. Here you can substitute positive values, negative values, fractional, negative, rational, irrational, any value. So the domain can be minus infinity to infinity. Okay, and all the exponential laws that we have discussed before are satisfied for this natural exponential function also. See, we have discussed, right? E power x into e power y will be e power x plus 5. Similarly, if there is division, then it will be x minus 5. E power x whole power y will be e power x y, and so on. All the properties that we have discussed in the exponents, all the laws of exponents, will be satisfied by this natural exponential function. See, there is no difference. I mean, the difference is very small. In the exponential function, the base can be anything. Okay, this natural exponential function is just a part of that exponential function where we fix the base. The base is e. We have fixed the base, so that is a natural exponential function. Okay, now let's discuss composite functions. See, basically the composite function is combination of two functions, something f of x and g of x. Okay, basically this is this can be written in the form of combination of two functions, f of x, f of g of x. This is how we represent a composite function. See here in the diagram makes it more clear. We are having, okay, so here, for suppose we are having x, this is a, and this is b, this is c, this is x, and on applying the function f of x, we'll get some f of x value here. And now on applying g of x function for this f of x, we get g of f of x. This also can be written as g of f of x. So this, both the representations are correct. This is how basically we represent a composite function. And remember, f of g of x is not equal to g of f of x. Okay, let's take an example for your understanding, for your better understanding. For suppose f of x is equal to x square and g of x is equal to x minus 1. Now we have to determine what is f of g of x. Sorry, let me write it clearly. What is f of g of x and g of f of x. Okay, so how do we actually determine this? See, first let us draw the diagram again, that makes you more clear. See, here we are having x. Let me use another color. On applying the function g of x, we get x minus 1, right? So now for this x minus 1, we are applying the function f of x. That means we write x minus 1 in the place of x. This will be x minus 1 whole square. So f of g of x is x minus 1 whole square. Similarly, if we try for g of f of x, this is x. On applying the function f of x, we get x square. Now on applying g of x function for this x square, that means we are substituting x square in place of x. So we get x square minus 1. So f of g of, wait, let me erase it and write it clearly. G of f of x is equal to x square minus 1. This is x minus 1 whole square and this is x square minus 1. This is how we actually determine the f of x and g of f of x values. Okay. So now, how to determine the domain of the composite function? See here, the domain for this composite function may not be equal to the domain of g of x and the domain of f of x. The domain will follow, there are some restrictions on the domain. See, for example, here we are finding the domain of f of g of x. Then x must be in the domain of the g of x function and the g of x must be in the domain of this f of x function when this is the case of f of g of x. Now for example, we are determining g of f of x, then x must be in the domain of f of x and this f of x function must be in the domain of g of x. See, remember, this belongs to representing the domain of f of x and the domain of g of x. So these are the conditions for the domain for a composite function. Following these rules, we will determine the domain. So now let's see an example that gives you a clear picture. For suppose f of x is root x, g of x is x square, wait a minute, 1 by x square minus 4. Okay, now we have to determine the domain for f of g of x and g of f of x. Okay, first thing, let's find out for this. See, what is the condition? X must be in the domain of g of x. So what is the domain of g of x? Here the x square minus 4 term must not be equal to 0, because if it is 0, then this g of x will become undefined or cannot be determined. So x square minus 4 must always not be equal to 0. That means x is not equal to minus 2 or 2. That means the domain is minus infinity to minus 2 union 2 to infinity. This is for g of x. Now this g of x function, see, this g of x is 1 by x square minus 4. This must be in the domain of f of x. That means 1 by root over, so this will be root over 1 minus x square by 4. So here for the root functions, the main thing is this term must always be greater than 0 and it must be defined. See, for x, this term to be greater than 0, simply x minus 4 must be greater than 0 and x minus 4 must not be equal to 0. That means strictly this must be greater than 0 itself. So the x values can be greater than 2 and less than minus 2. So the domain of this function f of g of x is minus infinity to minus 2 union 2 to infinity. This is how we determine the domain for composite functions. Okay, now let's discuss about inverse functions. What are inverse functions? See, previously we have discussed the composite functions. Okay, now if this condition is satisfied, f of g of x is equal to g of f of x is equal to x, then we can say f of x and g of x are inverse to each other. Previously I have told that this condition will not be satisfied. Okay, just make a correction. This will be satisfied only in case of inverse functions. Okay, so now we have another property here. For example, let's say this is the graph this is the graph of some certain function f of x. Then the graph for this inverse would look something like this. That means simply this is the mirror image with respect to the line y is equal to x. Okay, so the properties of these inverse functions are, this is one of the property. If there is we have the graph of f of x, then the graph for that inverse function is just the mirror image with respect to the line y equal to x. Okay, now for suppose here we are given function f of x is equal to 2x plus 3, and now we are asked to find the inverse. Okay, inverse means f inverse of x. Okay, we are asked to find this. So now how do we solve this kind of questions? See, first here we given y is equal to 2x plus 3. Now interchange x and y. That will give you x is equal to 2y plus 3. Now solve for y. Okay, that means x minus 3 is equal to 2y. That implies y is equal to x minus 3 by 2. This will give you your inverse. F inverse of x is x minus 3 by 2. So first thing what we have to do is interchange the x and y, then solve for y. So now the inverse of this function is x minus 3 by 2. Okay, and here to verify whether the answer is correct or not, you can check it. Like we have discussed the property before, f of g of x will be equal to x if these two are inverse to each other. So now see, the inverse we got is x minus 3 by 2. Okay, the function f of x is 2 into x plus 3. This is x value, 2 into x plus 3. Now solve this. X minus 3 plus 3. We got x. And if we solve g of f of x, that means in place of x we substitute 2x plus 3. 2x plus 3 minus 3 by 2. That will give you 2x by 2, that is x. See here, f of g of x and g of f of x both are giving you the x value only. Okay, this is how you verify whether the determined inverse is correct or not. And here let's see some applications. See here, for suppose you are given f of x is equal to some x minus 2 and g of x is equal to is x plus, just a minute. Okay, see, g of x is x square. So now we are asked to find the inverses of these two functions. See, what I have told first, interchange. So y equal to x minus 2. Now interchanging y and x will give you x is equal to y minus 2. Solve for y, that means y is equal to x plus 2. So x plus 2 is the inverse of this function. Whereas coming to g of x, so simply again y is equal to x square. Interchange x and y, that means x is equal to y square. That means y is equal to plus or minus root x. Okay, see here, here we are getting two different possible values for same y value. That means x square function is not 1. Okay, we have discussed this point before also. And see here, for same value of x, for example, if you substitute x is equal to 4, you get plus 2 and minus 2. You substitute x equal to 9, you get plus 3 and minus 3. So for same value of x, you're getting different values of y. That means in such kind of functions, we say inverse does not exist. Or to make the inverse to exist, we have to restrict the domain. See, for example, if we restrict the domain to only the positive positive r values, only the positive real numbers, then what would happen? This minus, there would be no minus, right? There would be no minus. Only plus value exists. That means now we are having unique values. So we can make the inverse function, we can make the inverse exist in restricted domain conditions. Okay, that means from this we can derive a conclusion that all the functions may or may not have inverse. Okay, that if you are having a function, that doesn't mean that the inverse must exist. We can make the inverse exist in some restricted domain conditions, and in some cases it may not be possible even. Okay, every function will, the statement we can take as the function may or may not have an inverse. That we have to determine and check like this, and we have to make the certain adjustments based on the required conditions. Okay, thank you. That's all for this lecture, and let's meet in the next lecture.